Took the last plane out of Saigon. Okay, we're live. All right, limiting reagents or limiting reactants. Some things are cheap, table salt, air. Some things are not, iridium, toner. So unless your reactants have been perfectly measured, one of them is going to be present in excess. The other one will be the limiting reagent. That's if you have two reactants. If you have three, then two of them will be in excess, and one of them will be the limiting reagent. So it's called the limiting reagent or limiting reactant because it determines how much product you can make. It puts a limit on the amount of product you can make. When I do this, I'm pretty much always going to call it limiting reagent just because that's how I learned it back in high school and college. Your book calls it a limiting reactant, I'm pretty sure. And when I write these out, I'll be using LR to denote a limiting reactant and XS to indicate that something is present in excess. There's some of it left over. Okay. So let's talk about water. If you mix 5 grams of hydrogen and 15 grams of oxygen, which one is the limiting reactant, and how many grams of water can you make? Okay. You cannot judge this based upon the masses. Once again, you always have to convert to moles. There are a couple of different ways you can do this. This is the way I prefer to do it. Let me bring up the paper. Okay, so 2 hydrogens plus 1 oxygen yields 2 waters. All right, so we have 5 grams of hydrogen. We have 15 grams of oxygen. Okay. This is the way I like to do limiting reactants. There are other ways. So first up, you convert both to moles. So 2.0158 grams per mole for hydrogen and 31.998 grams per mole for oxygen. So when you do that, you're going to end up with, I believe this is 2.48 moles. And this is going to be it's going to be a little bit less than 5. All right, let me bring up the calculator. First up, 5 divided by 2.0158. Yep, 2.48. And then 15 divided by 31.998. Yes. All right. So that's 0.4688 moles. All right. So this is one reason why you can't judge based solely on maths, because that 5 grams of hydrogen is a lot more in terms of moles, and that 15 grams of oxygen is quite a bit less. So you always have to convert to moles, but that is not enough. There is an additional step you have to take, because hydrogen gets used up faster than oxygen. You use up 2 moles of hydrogen for every 1 mole of oxygen you're going to use up. Okay. So in addition to converting to moles, you also have to standardize it to the reaction. So it's not just a matter of converting to moles. You then go through and divide by the coefficient from the reaction. So 1.24, 0.4688. Okay. So now we see that in terms of the rate at which they get used by the reaction, it's still the oxygen. The oxygen is going to be our limiting reactant, and our hydrogen is present in excess. Okay. So even though hydrogen gets used up twice as fast as oxygen, there's just so much more hydrogen than oxygen that it is still going to be present in excess. So now that we have our limiting reagent, we can go through and we can find out how much water we can actually make. Okay. And then, so we go back up here and we grab this guy. It's the same number, but it won't always be. So we come back up here, we grab him, and that is what we use for our stoich. And there, it's just perfectly normal stoich, 0.4688 moles of oxygen times 2 moles of water for every 1 mole of oxygen times 18.02 grams per mole for water. Now, the reason I make it a point, I'm saying come back up here and grab this, because these numbers might be different and that would screw things up. So always use those. All right, so when you do that, 0.4688 times 2 times 18.02 means you're going to produce 16.90 grams of water. So we started with 5 grams of hydrogen, 15 grams of oxygen. When we're done, we have 16.90 grams of water, and we're going to have some hydrogen left over. So it would be a perfectly valuable question to ask how much hydrogen would be left over. And the answer to that is actually fairly simple. Whatever got used went in here. So we used 1.9 grams of hydrogen, which means we have 3.1 grams of hydrogen left over. All right, well, let's move on to our next example, ruining pennies. I call this ruining pennies because the core of a penny is now zinc. They're no longer pure copper. So you drop zinc into hydrochloric acid, you'll get zinc chloride and hydrogen gas. So we have 1.5 grams of zinc, 2.5 grams of hydrogen chloride. Which one is the limiting reagent? We haven't discussed solution chemistry yet, so I'm putting it in terms of grams. So first we need to balance the reaction. Okay, that's easy enough. Zinc plus 2 HCl yields zinc chloride and hydrogen. 1.500 grams, 2.500 grams. We convert to moles. So the molar mass of zinc, bring up the periodic table. Oops. Zinc is 65.38 grams per mole. Hydrogen chloride, I'm going to do the calculator for this one. 36.461. Yeah. Once again, bring up the calculator. 1.5 divided by 65.38. 0.02294 moles of zinc. 2.5 divided by 36.461, 0.06857 moles. And we're still not done. Oops. Okay, that wasn't the cat, that was me. All right. Because now that we know how many moles of each we have, we need to compare them in terms of the reaction, not just in terms of moles. So divide this one by 1, divide this one by 2. This number is not going to change. This one will. But even though it gets used up twice as fast, there is still more hydrogen chloride than zinc in terms of the reaction, which means that this one is our limiting reactant. The reason I like to do it this way, mostly it's because it's the way I've always done it, but it works better in terms of if you had like 3 or 4 reactants, you could compare them all side by side that way. Because you can also instead compare them more directly. So say we have 1.500 grams of zinc. We can just say how much hydrogen chloride do we need for that. So we convert it to moles. And then we do the stoichiometry. We use 2 moles of HCl for every 1 mole of zinc. And then we convert it back to grams. 36.461 grams per mole HCl. And when we do that, we plug it into our calculator. 1.5 divided by 65.38 times 2 times 36.461. The answer we get is 1.673 grams of HCl. So what we see there is 1.5 grams of zinc will need 1.673 grams of hydrogen chloride, and we have more than that, which means that this is our limiting reactant and this is present in excess. So you can do this either way. Another reason I like this is because once you do convert to moles, divide by the coefficients, it's just which number is smaller. This one, I think, I mean, this is perfectly fine. Just it might be confusing for you. But if this is the way you want to do it, then absolutely do it this way. Remember, I don't care how you get the answer so long as you consistently get the right answer. So if this works better for you, do it this way. Tell me to go to hell quietly in your head. Don't say it to my face. I might cry. All right. So here's another example. Nitrogen plus water. Hypothetically, you could make dinitrogen tetroxide and hydrogen gas. So if we have 10 grams of nitrogen and 12 grams of water, how many grams of dinitrogen tetroxide could we make? This would be, with a 100% yield. And yes, we can and probably will combine limiting reactant problems and percent yield problems and get all sorts of wonky crap out of it. So once again, we balance the reaction. All right, that was quick. Okay, so, yep. All right, so we have 10 grams of nitrogen, 12 grams of water. It's sort of starting to look like the water is going to be our limiting reagent, but let's play it safe. So 28.02 grams per mole, 18.02 grams per mole. 0.3569 0.6659. Yep, still looking like it's going to be water because now we divide by 1 and we divide by 4. 0.3569 versus 0.1665. Yep, water is definitely the limiting reactant. And now we can see once again why I'm stressing use this number because it's significantly different. All right, so now we can use this to calculate how many moles of the dinitrogen tetroxide we could make using this really weird reaction. All right, 0.6659 moles of water times 1 mole of N2O4 for every 4 moles of water times the molar mass of dinitrogen tetroxide. So let's see, that is 14.09 times 2 is 15.999 times 4. 92.014 grams per mole. So 6659 divided by 4 times 92.014 is 15.32 grams of N2O4. And how much nitrogen? We'd have about 7 grams. Well, 6.68 grams of nitrogen left over. I don't know that they would ask. They could. So we started with 12 grams of water. We ended up with 15.32 grams of our product. So that means we used 3.32 grams of nitrogen in the reaction. So we started with 10, we used 3.32, we're left with 6.68 grams. That's all. That's something that you can do when you only have the 2 reactants. If you have more than 2 reactants, then you'd actually have to do stoichiometry and get a little bit fancier. All right, I think that's nope, one more example. Whoa, I tossed some more stuff in there. Okay, this time it's also a % yield problem, and we have an impure reactant. So in this case, instead of using pure iron ore, pure rust, basically, I said that it is 20.24% hematite. The rest of it would be quartz, probably. Actually, I have no idea. I shouldn't say that. I'm not a geologist. What the hell do I know? All right. Anyway, 20.24% hematite and 0.5 tons of carbon. And the process is 95.85% yield. Okay. So we're going to need to do a lot for this one. First, we're going to need to balance the equation. Then we're also going to need to find out how much of the iron ore is actually our Fe2O3, because only 20.24% of this 2.25 tons is actually iron. So, and then once we have the actual amount of that, then we can compare the iron ore and the carbon mole to mole to find the limiting reactant. So, boop. All right, let's bring the camera over this way. There we go. It's a little bit more comfortable for me. All right, so balanced reaction, it'll be easy enough. Let's do the iron ore bit first. 2.250 tons times 0.2024. Okay. Of our 2.25 tons, only 20.24%. So 20% of something, it's okay. So it's a little bit more than 1/5. So how much of our ore is actually the iron oxide? 2.25 times 0.2024, 0.4554, 0.454 tons. And that's how much of the stuff we have is actually iron 3 oxide. Okay, 20% of that, a little bit more than 20%, gives us the 0.4554. So now we can compare this number to the amount of carbon. So 2 Fe2O3 plus 3 carbon yields 4 iron plus 3 CO2. So we have 0.4554 tons, and we have 0.5000 tons. So let's go ahead and convert those to grams. That would be 4.554 times 10 to the 5th grams, and 5.000 times 10 to the 5th grams. Yes, okay. I was just double checking my math in my head. Because 1 ton is 1 million grams, so half a ton is 500,000 grams, or 5 times 10 to the 5th. All right, now we can convert to moles. 159.629 grams per mole, and 12.011 grams per mole. So 455,400 divided by 159.629 is 2853 moles. 500,000 divided by 12.011. 41,630 moles. I'm thinking that we're going to have an excess of carbon. that is a lot of moles of carbon. All right. But now, just to be sure, we're going to go ahead and divide by 2, divide by 3. This is going to be 1427, and this is going to be about 14,000. 13,880. So yes, the iron is our limiting reactant. Or the iron oxide, I should say. And then I asked, how much iron can we produce with a 95.85% yield? All right, so now that we have our limiting reactant, we can go ahead and calculate the theoretical yield. Okay, let's see if I can't. Yeah, there we go. All right, so all right. So 2,853 moles of iron 3 oxide times 4 moles of iron for every 2 moles of iron 3 oxide. Times, let's see, 55.845 grams of iron for every 1 mole of iron. This will get us our theoretical yield, 2853 times 2 times 55.845. Means that we're looking at 318,700 grams of iron, or 0.3187 tons of iron. So this is our theoretical. So if our percent yield is 95.85%, what's our actual yield? So percent yield is equal to actual over theoretical. So actual equals percent yield times theoretical. So our theoretical yield was 0.3187 tons. Our percent yield was 95.85%. So we throw that into our calculator. So times 0.9585 brings it down some, not a heck of a lot, 0.3054 tons of iron. This is our actual yield. So that problem is a lot of work. I think that's a bit more involved than they're likely to give you on a test. My experience with tests is that they typically want to ask you one thing at a time. So they'll ask you to balance the equation, or they'll ask you to find a limiting reactant, or they'll ask you to do something with percent yield. They wouldn't necessarily throw them all at you on a single problem like I did here. But, you know, getting good at doing all of this stuff requires practice, so you might as well practice everything all the time. All right. And with that, we are done with this section, and my throat is really dry from talking. So I am going to go ahead and call it for the evening, and wish you good luck on the lab, and I will see you this coming week, where we'll do a little bit more practice in class. See you around.